Welcome to our technical webinar on natural or geologic hydrogen. GEIOS Technologies and AIDEN Digital Labs will present the scientific basis, exploration methods, engineering workflows, and commercialization pathways for geological hydrogen, drawing on our backgrounds in advanced geothermal systems, subsurface geology, and nanotechnology-enabled sensing. Today's market is dominated by gray hydrogen due to its low cost but high emissions, while electrolysis remains capital and power-intensive. Natural hydrogen offers a third pathway, molecules produced by the Earth itself, with the potential to undercut electrolysis LCOH while dramatically reducing life cycle emissions, provided purity, deliverability, and scale are achieved. Natural hydrogen is H2 generated by crustal processes and stored in subsurface traps or migrating through fracture networks. Typical reservoir gases include H2 with N2, He, and trace hydrocarbons. Our objective is to detect, appraise, produce, and integrate these resources using established subsurface engineering adapted for hydrogen's unique properties. By avoiding electricity-heavy production, natural H2 can shift cost curves and accelerate decarbonization across ammonia, refining, steel, and heavy transport. If we validate continuous generation and secure reliable trapping, we gain an ultra-low carbon feedstock compatible with existing gas infrastructure and future H2 networks. For decades, natural H2 occurrences were viewed as curiosities: continuous flows documented in West Africa, circular surface features in Brazil, basement-related seeps in Eurasia, and modern appraisal programs have now reframed the field from anecdotal to systematic exploration with emerging standards. Prospective settings occur on multiple continents: cratonic shields, ophiolites, rift margins, and basement chord basins. The diversity of plays requires integrated geoscience, lithology, structure, heat flow, seal presence, and fluid evolution to rank targets before drilling. Decarbonization scenarios require hundreds of megatons of hydrogen by 2050. Natural hydrogen, where viable, can offer domestic low-cost supply, reducing exposure to imported fuels and mitigating power price volatility inherent in electricity-derived hydrogen. Countries with onshore natural H2 potential can internalize supply chains, anchor industrial clusters, and stabilize long-term pricing. Co-production of helium, a critical strategic gas, can materially improve project economics and national resilience. In ultramafic rocks, fee-bearing olivine and pyroxene react with water to form serpentine, brucite, and magnetite, releasing H2. This reaction, dominant in ophiolites and ridge environments, depends on temperature, water availability, and rock fabric. Onshore abducted belts are priority search areas. Radiolysis in uranium, thorium, and potassium-rich granites, oxidation of iron sulfides, cracking of hydrocarbons, and frictional processes along faults also produce hydrogen. Each mechanism implies different thermal regimes, spatial distributions, and co-gases, all of which inform exploration models. Commercial accumulations require source in time, migration pathways, an effective trap, and preservation against losses or microbial consumption. Fractured basement and damage zones provide permeability. Seals include evaporates, clays, and intrusive bodies that maintain column height. Alkaline vents like Lost City reveal stable H2 generation at moderate temperatures, while high-temperature systems showcase metal H2 coupling. Though offshore developments are complex, these analogs validate geochemical pathways and guide isotopic and mineralogical fingerprints onshore. Long-lived flows in Mali, promising wells in Australia, and Brazilian circular features confirm onshore detectability. These natural laboratories underpin emerging type curves for deliverability, decline behavior, and pressure management in fractured systems. Retention depends on trap geometry, seal integrity, and microbial chemical sinks. We evaluate redox conditions, mineralogy, pore throat distributions, and fracture connectivity to predict preservation timescales and production potential. Fairy circles, vegetation stress, microtopographic lineaments, and soil gas anomalies provide reconnaissance signals. AIDEN's distributed sensors and mobile flux platforms enable rapid ppm/ppb mapping to focus subsurface investment, where signals persist and correlate with structure. Global in-place resources may be substantial, but recoverability hinges on trap frequency and scale. We treat early programs as probabilistic portfolios, with thresholds on flow, purity, and connected volume before moving to appraisal. Since 2024, multiple national initiatives and private explorers have formalized licensing and standards. Cross-disciplinary teams, geologists, reservoir engineers, geochemists, materials scientists, are converging to create a coherent value chain for exploration and production. Prospectivity varies with tectonic history and lithology. Economic robustness improves significantly where helium is recoverable. Coupled H2-He projects can offset separation energy and improve IRR, particularly in early-stage basins. We fuse remote sensing, structural lineament analysis, UAV-based spectroscopy, soil gas transects, passive flux monitoring, magnetic/gravity, and shallow stratigraphic probes. Machine learning ranks prospects by multi-sensor concordance, seal likelihood, and access. Peer-reviewed studies now cover generation kinetics, isotopic signatures, microbial sinks, and field production. Our work adheres to rigorous QA/QC, replicate samples, blanks, calibrations, and statistical confidence, so results translate into bankable engineering decisions. Published wells show multi-year flows at modest wellhead pressures, implying either large connected volumes or ongoing generation. We apply geothermal grade monitoring, pressure temperature gas composition, to develop decline models and completion designs. A maturing ecosystem is aligning sampling protocols, drilling safety, and reporting. GEIOS contributes geothermal class well architecture, while AIDEN contributes standardized field metrology and data models, so results are comparable across programs. Permitting frameworks must address hydrogen's diffusivity, embrittlement risk, and ignition characteristics. We implement groundwater baselines, intrinsically safe equipment, continuous leak detection, and emergency response planning aligned with industrial gas standards. We need better generation rate models by lithology, fracture network transport simulators for H2, and standardized petrophysics for fractured basement. Materials research, metallurgy, seals, elastomers must reflect hydrogen's small molecule behavior. National surveys, universities, and industry labs are rapidly expanding experimental data sets. We partner on mineralogical tests, tracer work, and reactive transport simulations to close uncertainty in source, migration, and sink terms. Natural H2 reduces CapEx and power intensity versus electrolysis. With favorable geology and sensible midstream, projects can target competitive LCOH, pipeline tie-ins, or near-site chemical conversion, further improve delivered cost. Well-to-gate footprints can be very low when operations use renewable power and best available separation. Land and water intensity are modest, with no process CO2 if separation trains are powered cleanly and venting is eliminated via closed-loop handling. Domestic natural H2 can anchor clean industry hubs, green ammonia, e-fuels, and H2DRI steel, while enhancing grid stability through sector coupling. This is not only a cost story, but a sovereignty and resilience story. Steel becomes competitive when H2 approaches approximately $2 per kilogram and supply is stable. Ammonia is an immediate offtake with mature logistics. Heavy transport and maritime can benefit through ammonia or compressed H2 corridors where safety cases are robust. Current technical success rates are modest. Disciplined portfolios are essential. We stage capital, low-cost surface screening, then shallow proofing, then slim hole or pilot wells, with defined gates on purity, flow stability, and reservoir connectivity. Source attribution can be multi-mechanistic in one basin. Microbial sinks vary with redox and moisture. Seal integrity can be episodic along faults. Continuous monitoring and conservative engineering margins manage these uncertainties. Hydrogen requires attention to embrittlement, leak-tight seals, and gas loss control during drilling. We adapt geothermal class designs, material selection, cementing, pressure management, and add real-time downhole H2 sensing to protect integrity and quantify deliverability. Exploration to appraisal programs often require $10 to $50 million per prospect. Initial developments can exceed $100 million. Early projects lean on equity and strategic partnerships. Offtake, helium credits, and infrastructure sharing can unlock competitive debt. Transparent baselines for air and water, open data on leaks and noise, and proactive emergency planning build trust. Clear communication with landowners and communities reduces delays that otherwise erode project returns. Post-discovery, we optimize completions for flow and purity, manage drawdown to avoid water influx, and design for pressure stability. Surface facilities emphasize intrinsically safe operations, continuous gas quality assurance, and remote monitoring. Depending on composition, we deploy membranes or PSA for H2 bulk separation and cryogenic trains where helium value justifies it. Hybrid schemes minimize kilowatt-hours per kilogram while meeting product specs and oxygen-free safety requirements. Liquefaction imposes deep cryogenics and significant energy demand. Compression is cheaper but distance limited. We therefore prioritize pipeline integration, near-site conversion to ammonia or methanol, or storage in suitable salt caverns where available. Processing energy, compression, separation, and storage must be planned holistically. We combine on-site renewables, grid interties, and battery buffers to meet safety-critical continuity while keeping carbon intensity and OPEX low. Near-term, AI-guided prospecting, improved field metrology, and H2-compatible materials. Medium-term, integrated H2/He recovery and lower energy separations. Long-term, regional storage networks and industrial hubs that absorb variability and scale. A realistic path is exploration scale-up this decade, first multi-field developments early next decade, and maturing supply chains by the mid-2030s. Standardization, data, safety, contracts will compress costs as experience accumulates. GEIOS Technology specializes in advanced geothermal and subsurface systems, high-integrity well architecture, thermal systems, and reservoir surveillance. AIDEN Digital Labs contributes sensing, AI analytics, and nanotechnology that sharpen detection, reduce uncertainty, and accelerate certification. Together, we deliver end-to-end programs, from basin screening and pilots to separation design, HSE, and route to market. Thank you for joining. We invite geological surveys, universities, mining and energy operators, and strategic investors to collaborate on pilots and data sharing. For technical workshops, data rooms, or joint field campaigns, contact our GEIOS and AIDEN teams. We're ready to co-design credible, responsible natural hydrogen developments at scale.